I'm very happy that I could come here and they gave me opportunity to come here and present my work in this network workshop. So today I'm going to talk about this optimized evolution of networks, and this work has been done in collaboration with my PhD student Priyaditi Pradhan and Sanjeev, who has finished his PhD and now he is postdoctorate in Denmark. So this was work he started with Sanjeev and then we are still doing with Priyaditi. So this work, this revolves around network spectra. Of course, Professor Bhatte, in the morning, he already introduced that what is the meaning of eigenvalues of the networks, like in the school and as well as in today's morning talk as well. So this talk will revolve around three things. One is network spectra, second is optimization, and third is this multiplex or multi-layer networks. And the prime aim of this work, which I'm going to present today, is regulating properties of one layer or one network by appropriate multiplexing. Okay, so this entire thing revolves around these three components: spectra, optimization, and multi-layer. So single layer networks means one types of interaction, which all of you have already been introduced and exposed in this school and the workshop. So you have one type of interaction, and I will give certain examples to introduce this multiplex or multi-layer network. But there may exist more than one type of interaction among the same unit, and this is the philosophy behind. Like for instance, now the examples which are here, that will make it more clear. So a multiplex network or multi-layer multiplex network, this is the mathematical definition, is a set of nodes interacting in m different layers. Like here m is equal to 2, so they are interacting in 2 different layers, and they may have different network property in each layer. For example, like one example which you can very easily associate yourself with, that is a social network. So you are like same set of the people which right now we are here in the room, we may be having Facebook network among ourselves based on, maybe that is more like based on your friendship, etc. And the Twitter network, which is maybe directed also, of course. So, but the point here is that the Twitter network, maybe the properties of this Twitter network among the same people may be different than the Facebook network. You may be also be thinking that for Facebook, you may having the friendship connection in Facebook with one person and may not follow that person in the Twitter. So you may have same people may have different types of interaction and different layers. And transport network, for instance, like if you talk about a transport network of a country, we have one layer, suppose it is made of flight connectivity between different cities, and one layer maybe with the train connectivity. And you may find that flight connectivity may not be there if cities are very nearby, where the train connectivity may be there. So obviously in transport networks, different layers and the same cities. Cities are the nodes, and the connections maybe if you have a flight connectivity or if you have a train connectivity, and you can very well visualize that train networks may be very different than the airport network or flight networks. And human brain also, different brain regions can be connected by functional or structural kind of connections, and they may be different. And the point here is that the activities of one layer that affects the dynamical behavior of another layer. So I have this thing in another slide. But before that, this is the transport system as network, and this is a single layer representation. And where this gray line that represents passenger flow. So this is the only taking care of airlines. And in the multi-layer, you may have, this is multi-layer. So this is you have yellow, which is showing the tram connectivity. This is the metro connectivity, and this is the white nodes, the bus connectivity. So it's a multi-layer transportation system. And this is for Madrid. So this is, I have taken, like this is a picture which is available in the internet, and this is constructed using the real data. So this is a multi-layer, and these lines, they are representing like how activities in this layer, suppose there is a strike in tram, how does it affect people who are using metro or people who are using buses or vice versa. So this interlayer connection, they are not physical connection, they are simply saying that how network change in one layer affects the dynamical properties of the like number of people boarding metros, how it affects this layer. So that is the meaning of this interlayer connection, which is not the physical connection, but it is showing the impact of one layer on another layer. So multi-layer frameworks provides understanding to various dynamical features of those systems which are beyond the limit of single layer. And the point here is that ignoring impact of multiplexity, we may get wrong predictions of the behavior of this layer. For instance, a strike in bus service, which may be this layer, may result in overloading the air or rail traffic. So if we are ignoring the connectivity of this layer, we may not be able to understand the sudden increase or decrease in the activities of this layer. So we may not be able to predict. So this is one of the work where we have done with the synchronization, but today I'm not going to talk about the synchronization. So the point here is that, so this is a drawback which is written here, that a strike in, like, we cannot predict. So if we are ignoring the impact of multiplexing, that may lead to the wrong prediction of first layer if we don't consider second layer. But now this we can use as our benefit. It means we can control maybe the properties of this layer by changing the properties of this layer. So we can control properties of entire system or one layer by tuning the structural properties of only one accessible layer. Like for instance, like these are examples. Of course, I am not working on any real world data. I am not going to show any real world data kind of thing, but this is just to motivate you. So like for example, if you want to have a better transport system of a country, it's very difficult to put one railway track, but it's easier to reroute some of the flight. So flight connectivity perhaps, or we can increase some flight, or we can have flight between two different cities. So we can change the structural properties of flight network rather perhaps more easily than the putting up new railway line. So in that manner perhaps, so one accessible layer maybe here is the flight or vice versa. So we can control the properties of entire system by tuning structural properties of only one accessible layer, and this is the entire motive of my work. And right now I am focusing on the eigenvectors. So, and I will show, so right now we are putting the eigenvectors, we are putting focus on the eigenvector localization. And why eigenvector localization? Because it has diverse application ranging from detection on influential node in a network, like which is the very important node, to disease spreading, and a lot of literature which is already there. And I have here written few of them which I found very interesting and useful, or which are landmark. So I'm talking about here, I'm focusing only the principal eigenvector, and I will introduce that what is the meaning of principal eigenvector of a network. So principal eigenvector, which is the eigenvector corresponding to largest eigenvalue. So principal eigenvector is useful for getting insight into propagation or restriction of perturbation in underlying system. It provides insight to disease spreading. So there are some work on the mutualistic ecological networks where also PV localization has been shown to provide insight that how perturbation in a network propagates in the system. And the brain networks also, it has been used in Google matrix. Now it has been recently been used a lot in the Google matrix by Stinsky group, this principal eigenvector. And of course this detection of multi-layer temporal network, which is similar as the detection of communities in the single layer. So this is a simple extension of that thing. And now let me introduce what I mean by the principal eigenvector. And I am not going to talk about any of these applications. Again, this is, so my today's talk is just at the fundamental side. It may have, right now we don't have any, we have not shown any applications. We have applications in mind, but we have not showing any applications. So these are just for the motivation again. So now this is suppose a network, and this is the adjacency matrix depiction of this network, where 0 means no connection and 1 means connection. So I have very simple representation of complex network in terms of adjacency matrix. 0, 1, unweighted, binary entries, very simple, undirected network. I am not talking about directed network right now. So undirected network, eigenvalues are real. So eigenvalues of this kind of adjacency matrix, that is known as the spectra of the network. So if we have n is the dimension, then we have n eigenvalues, and these are the corresponding eigenvectors. And eigenvector corresponding to the largest eigenvalue, that we are calling the principal eigenvector. So if we have lambda 1 is the largest eigenvalue, x1, which is the eigenvector corresponding to lambda 1, that is the principal eigenvector. So this is for single layer. And multi-layer means now you have two different layers. So this is one layer. So A1 represents the adjacency matrix of layer 1. And A2, that represents the adjacency matrix of layer 2. And this I is nothing but this unit matrix, which is representing one-to-one connection between layer 1 and layer 2. And it is actually not physical connection, but it is just simply showing that how this layer. Yeah, you may have different number of nodes. You may have one-to-many connections also. So this is one of the, so this matrix may be very different. It may not be identity matrix. It can be full-fledged matrix. So this node may be connected with all of these nodes perhaps. So there may be all these variations, but all this framework that remains same. And you may have number of nodes which may be different. So for instance, if we make number of nodes here is different than this, then we can introduce here some of the isolated nodes. So my A2 matrix, that will change. If I introduce some of the isolated nodes, this matrix will change. So that remains, all this framework that remains valid, whatever matrix we are taking here. And this dx is the coupling strength on which this layer is interacting with this layer. This is a more generalized framework. And this EY is saying the relative coupling strength between this and this layer. So this layer may be strongly interacting. So they have more maybe flight connectivity between different cities and less connections of the trains or vice versa. So this layer may be having the weak interaction and this layer may be having stronger interaction, and EY is the measure of relative coupling strength of the. Yes, this is a more generalized thing. And we are talking about the eigenvectors. So again, the eigenvalues of now this matrices, which is called a spectra, and the eigenvector corresponding to this entire multi-layer networks, that is again, we will take the largest eigenvector corresponding to largest eigenvalue of this entire multi-layer networks, okay? So the same thing, whatever we had for single layer, we will calculate the eigenvalues and eigenvector corresponding to largest one, that will be PV. So this is for single layer and this is for multi-layer, the same thing. And we are interested in the localization of an eigenvector, and localization means few components of a vector take very high value and rest of the components they take smaller values, and I have mathematical definition here in this slide. So here xi is the ith component of the normalized eigenvector. So of course this is normalized, take unnormalized that, then also it's okay, we have to just divide it by something. So xi is the ith component of the eigenvector, and xk with k is equal to 1 to n. So this x1, x2, x3, xn, that is the eigenvector, and xi is the ith component of the PV eigenvector. So if we are taking this capital X1, so this is the PV, xi will be the ith component of the first eigenvector, and delocalized eigenvector will have component like this. Delocalized eigenvectors means all components of that eigenvector will be same, which would be 1 upon root n, because this eigenvector is normalized. If we take the square of all this component, that will give us 1. So for normalized eigenvector, for delocalized eigenvector, we'll have all the components which are same. It means all nodes have the same weight, same contribution in the eigenvector. And IPR of this kind of eigenvector would be 1 upon n, where the most localized one, that it means in the vector you have only one component which is 1 and all other components which is 0. So again it is normalized, and in that case IPR would be 1. So yes, this yxk, actually this is more generalized notation which we have used here, that is the IPR value. So if we have, I can actually draw a vector here, actually, this is, so now you have, so this is PV. PV means suppose x1 eigenvector, so 1 upon root n, 1 upon root n. This is now my eigenvector, which is the most delocalized, and if we calculate IPR, which we have denoted here as y of x1, x1 is the, y is the IPR of the first eigenvector, and if we just take the to the power 4, like this function if we take, then this would be 1 upon n. And the extreme end is the localized one. It means only one component is 1 and all other are 0. So 1 upon root n is coming because the one constraint is there, that xi is square, that should be equal to 1, I is equal to 1 to n. That's why you have 1 upon root n. So extreme case is that this is a localized one, and for localized one, your IPR, it means y of x1, that is equal to 1. So that is two different extreme cases for the localization and delocalization. But for a connected network, so this kind of case, like when you have yx1 is equal to 1, it means all nodes are isolated. And then that's why any information which is there in one node, that is there in that node and it is not spreading. So that is the localization. And for the regular graph, for instance, like globally connected network, PV will be completely delocalized because all nodes are equally contributing in the spreading of the information, for instance. But for a connected network, the IPR value that will lie between these two extremes. We will never able to find this completely localized case for which IPR is 1, because if network is connected. Unless we are having isolated node, we are never able to achieve the complete localization. And for globally connected network, we get delocalized PV, that is true. But for a connected random network or which is not globally coupled network, the IPR value that lies between these two extremes, which is 1 upon n and 1, okay? So now the problem here is that, now let me pose the problem, mathematical problem or computational problem. For given size, it means number of nodes. So right now I'm talking about the single layer network, and then I will show the same thing how we are doing with the multi-layer. So for given size, it means number of nodes and building cost, which is the number of connection. I am posing the question that what network structure will correspond to the most localized PV. So suppose given n and given number of connection, what network will you draw that you have most localized PV? Because I have already told that unless you have isolated network, we cannot have PV1. PV1 is the maximum localized state, but we cannot achieve that. So what could be the maximum value which you can get for given number of nodes and given number of connection? This is the first thing. And what is the network architecture? Because delocalized is easy to construct because we construct a regular network. Each node has the same kind of atmosphere, contributing same, then you have delocalization. But for localization, one can think of a star network, but in a star network, you have restriction between the number of connections and n. So NC is exactly equal to n minus 1. But here the problem is that given number of connections and given number of the nodes, what network architecture will correspond to the most localized PV. Okay. And this is not so straightforward because we have seen when it's for star network, when tree structure also has very localized PV, but that may not be maximum localized. You can always get a network. Yes. PV. Sorry?
Why are you interested in the most localized PV?
Because I have already actually given this bit of motivation that people have been interested in the localization of PV because that kind of network is very good to localize any information. For instance, like disease spreading in the system. That's why I said that we cannot immediately apply this thing, but motivation is that now disease is spreading. You want to localize the disease. This is the first thing, but the scheme which I am telling you doesn't work in that. That's why we need multi-layer thing, but we want to know whether something will spread or get localized. This is the thing, and PV has this power to tell you whether something, any dynamical, like random walkers on the network, which is very important for physicists, whether they are localized on particular section or they will spread without really performing the random walker experiment, just by assessing the network properties. So it has a lot of applications. And of course, whatever I am saying today is not going to be really applicable immediately, but it is the final goal. So now that is the question which we are asking, that what network architecture will have the most localized PV. So you can always construct very highly localized PV. Like you take a scale-free network, you will find that PV is, like IPR of PV is higher than the corresponding random network. Higher, but still you cannot say this is the maximum localized, okay? So this is now the theoretical framework. So for given size, given n is the size of the system, and NC is the building cost, it means number of connection. If we can enumerate all the possible configuration, then we solve the problem, because if we enumerate all the possible configuration, calculate the IPR, and then we find, okay, for this configuration, my IPR is maximum, and now this is my configuration, which is the best, and we can investigate the structural properties of those configuration. So problem is solved, but enumerating all the network configuration for given n and nc, if n is large and nc, even not large, even suppose you take only 20 nodes or 50 nodes, then it is computationally very exhaustive problem. If nc is not equal to n minus 1, if nc is equal to n minus 1 or very close to n, then you have tree graph or star graph, that is easier. but enumerating all the network configuration is completely exhaustive, and now this optimization things come into picture. So we formulate this problem through an optimization technique. So now here, this is a very simple optimization technique. One can have any variation of optimization, but this is the one of the very simplest one which we have used, and we have tried many other methods and it all seemed to work. So we construct a network which has a highly localized principal eigenvector using an optimization technique, and then this is a rewiring, and I think this process, not I think, like I know Professor Sinha has done fantastic work on the rewiring thing, and yesterday I missed her talk, but I think you guys have already some exposure of this network rewiring. So suppose now we have a given network. This is suppose our network, and and then adjacency matrix of this kind of network is suppose A, and we calculate the IPR value of principal eigenvector of matrix A. Now we rewire A's from this network. Rewire means we remove this A's, so which is this kind of, and we add somewhere else. So we select uniformly, randomly A's, and then we rewire that A's to some other pair of the nodes and calculate the IPR of this matrix. If IPR of this matrix is larger than IPR of this matrix, we replace our A by this A prime. So it's a very simple thing. So we keep on doing the rewiring, and then of course there are some methods, simulated handling, etc., which like we have to give some temperature, and we have to, in the beginning we have to give some noise, etc., so that we don't go into the local minima. So those things are there, but I am not going to details of the optimization process, but this is the scheme. So we keep on rewiring such that our networks gets improved, and we can keep on getting the localization of PV. So very simple method, and this is like, so we have this network, so that was metric diagram or for smaller setup. So we remove an A's and add it somewhere, and IPR at t plus 1, and this is meaning of t here, like evolution, IPR at t plus 1 greater than IPR t, then we accept this one, otherwise we search for another A's rewiring which can give to IPR at t plus 1 larger than IPR at t. And these are the results. So here this is the evolution time, and here it is like we have evolved up to the order of 10 to the power 3 because it takes a lot of time in getting saturated. So we start with the initial network, and yx1 is nothing but the IPR of the largest eigenvector. So in the beginning, since we start with the random network, but final result is independent of what initial network architecture we have chosen, but just for showcasing the result, here we have, here it is starting with the Edosony random network. You can see the IPR is very small, it is close to 0, which is not surprising because Edosony random network, you will have all nodes contributing almost same because all nodes have the same average degree and all different centrality are same. So you have IPR value for Edosony random network which is very small, and as we are evolving, so x-axis is the evolution in terms of the A's rewiring. So as we are doing A's rewiring, you can see this IPR is increasing and getting saturated. So in the beginning it is slow increase because optimization is taking too much time in finding out the right path, and once it is really found out appropriate nodes which is leading to entire evolution of IPR, it is very fast, and all these designs are very interesting, but okay, I am just focusing on the prime results. And then finally we are getting saturation. So finally now we have got one network structure which has IPR as high as close to 0.16, and it is actually very high because our delocalized network has IPR which is very close to 1 upon n or 3 by n, as the random matrix prediction says, that you have the random matrix, and if you take the IPR of any vector, that would be close to 3 by n. It's the order of 1 upon n, and now here we are getting approximately, which is very close to the order of 1, so which is very highly localized network which we have achieved. And here all the
depends on the number of nodes and the
1 upon n, that's what 1 upon n is the, but
it will also depend on the
number of A's, number of nodes. I have some pictures for the number of nodes also, and number of A's also it will depend, because if you have too large number of A's, you cannot really have too large number of localization. So a sparse network, yeah, is right. So sparse network you can rewire to get very localized network, but if you have dense network, number of combination permutation also becomes smaller, and then there may be limitation that to what localization you can go. So sparseness is here an important thing, yes. So these are all these things for a sparse network, because if you make dense network, you may not really increase the localization property that much, or it may take a lot of time because then you have more number of edges to rewire. So now here it is yx1. So our focus, we are only optimizing or rewiring the network using the spectral property keeping into mind, only IPR. And here we are only investigating that what happens to other property. We are not doing anything to largest degree. Kmax stands for largest degree. Average clustering coefficient of the network, degree correlation, degree clustering correlation, because there are the work which says that a degree clustering coefficient and PV clustering correlation, because there are the work which says that PV centrality is related with the degree centrality or clustering coefficient centrality. So we have just tracked all these results, and actual simulation were performed keeping yx1 in view. So this has to increase. There is no other way, because our optimization wants yx1 to increase. So that is the forced result, like which we want. And these are the consequences of forcing yx1 to increase. So first thing is that Kmax will increase. So one node will become central node, and which is not surprising at all, because in the star network also one node is having very large number of degree and all other nodes are smaller. So it means you can assume that any kind of information that will spend more time on the node which is having the largest degree, because information has more probability to come back to the largest degree node. So not surprising at all that one node will become having the very high degree, like a scale-free network. So one can start now thinking, guessing that what is the network which has all these properties present. So what might this network now look like? So one can think that, okay, Kmax is becoming very high, so it may be scale-free network, because in a scale-free network, one can think that largest node, largest degree is very high. Clustering coefficient is also increasing, which is also not surprising, because now we are having small motifs kind of structure, and information is spending more time there, perhaps getting trapped. So, and that is the meaning of we want information to be trapped, that is the meaning of localization. So CC is also increasing, that is okay. And degree correlation and all those things we have just investigated, and I am not spending much time because there is nothing much fruitful one-line message for this. So this is optimized evolution, and this is for different network size also. Actually we have performed the result, and then you can see that of course it is cannot increase much, 500, 1000, 2000, but as network size is increasing, you may have more, for sparse network you have more chances that you can get a better localized network. So this is initial IPR value, and this is the final IPR value, and this is as you are increasing as you are evolving the network. So this is for different network size, so this works, okay. And now we try to see that which model network it is corresponds to, because we found some properties that the final network should have degree, which is something like a scale-free kind of thing. One degree is very high and all degrees are very small. So we can construct actually one random network having the exactly same degree sequence as we got for the optimized network. Optimized network means final network. So that is known as configuration model. So we have constructed the configuration model of the optimized network. It means same degree sequence. And then we find that IPR is so small, it is approximately 0.05, whereas this is now we have 10 order more the IPR. So right now this IPR of the same degree sequence is very small, 0.05, where we have our IPR of the order of 0.15. So IPR of configuration model with the same degree sequence is very small. Now what we can see, since we saw that clustering coefficient is increasing, so there are algorithms that we can generate a random graph for the given clustering coefficient. That also we did, and again you can see that IPR is very small. In the previous graph, we found that this degree correlation that is decreasing. It means network is becoming more dissertative, which is also not surprising because star network is also very dissertative, and the star network has very high IPR value. So we thought, okay, maybe this property can capture or can tell us that why we are getting the localized network. But we constructed a network with the same degree sequence as of the optimized network, but random network. But again, we found that IPR is very small. So not a single model network can capture the property which we found in the optimized network, and IPR value is much lesser than the network created through the evolution. So now this is the picture of optimized network, which we did the simulation for very small network, a small size network, in order to see that what kind of network structure we get. So this is the initial network, and now this is the optimized network which we found. So optimized network consists of two parts. One is very small part, which is not globally connected, which is like a star, with very high clustering coefficient. So very high clustering coefficient is coming because of this part, because here you can see the triangles are there. So any information or random occurs comes here and it spends a lot of time because it has a lot of triangles here and it's very high degree. So this node is having very high degree. And then we have larger part of the network, which is something like the Idoswani random network. So this is random part, and this is the part which is having very high clustering coefficient, very high degree. So you start with any initial network, not ER network. Suppose we start with the network, suppose we break this network here and we start this part. Again we get the same thing. Or we break this network, start with this part and then evolve this thing. Again we get the same result. So irrespective of initial condition, your final optimized network is like this, and which we understood somehow what, but there are a lot of things which is, yeah.
Ratio between the number of...
So this is 1:3. So you have 70% or something like here and 30%. That is also very constant for all network size, for all network size and for all types of network configuration. Okay, and now we know that why that particular network size is coming, because this clue lies in the degenerate eigenvalues, which I will show now. So this optimized structure is robust against change in the initial network structure. And now, I think this is, okay. So now this is the something which is very interesting for me, and I think you will also find this point is interesting. So this is a network evolution. Yx1 is increasing, and now here I am including all the rewirings, not only those rewirings which is increasing the IPR, you know. So earlier result I shown when IPR was only increasing, I was only accepting those rewiring where IPR were increasing. But once we reach to this regime, what I did, I am now rewiring the nodes and just seeing the IPR value, that what is happening. And here you can see there are drops. It means for one single rewiring, it is possible that IPR is completely dropping from most localized to the completely delocalized. So here I am accepting all the rewiring. So for there may exist few rewiring that you make one rewiring and IPR is completely delocalized. So that is happening in intermediate as well. So this is the regime which we have got, and when we try to understand this thing, that is coming because of this degenerate eigenvalues. So what happens, this is the evolution. So in the previous slides, I conveyed a lot of structural properties I displayed, but here now we have largest eigenvalue and second largest eigenvalue which we are plotting here. And as network is evolving, keeping IPR is the only thing which we are increasing. What is happening that lambda 1 is approximately anyway fluctuating around whatever it is started, but lambda 2 is increasing and becoming degenerate. So this is R3 reason. So as soon as your network becomes completely localized, your two eigenvalues, they are becoming degenerate. And that is the thing, no matter from where you start with. It means it is the scale-free network. Right now this figure is for scale-free network. And a scale-free network, you know that largest eigenvalue is much higher than the corresponding ER network, because in a scale-free network you have largest degree very high and largest eigenvalue is bound with the largest degree. So you start with very high lambda 1, but here lambda 1 is decreasing and lambda 2 is increasing. Again you are getting degenerate eigenvalues exactly at the same point. R3 is the reason where you start getting saturation. So you start, and as soon as you get localized eigenvector, you have two eigenvalues which are becoming degenerate. We started CL again as initial network and perform the same thing, and again you got as soon as you are getting the localization, completely localized, you get two eigenvalues which are coming same, and that is the reason behind this drop of eigenvalues, I am not explaining right now. And this is some of the analytical derivations which we have also done in order to understand that this increase, that how this is increasing and how it is depending upon, because what we are doing, we are rewiring the network. It means we are changing the adjacency matrix and we are seeing that IPR is getting localized. So here we tried to establish that how this change in the eigenvector entries. So this is the eigenvector entries. So XR is the Rth eigenvector entry, XS is the Sth eigenvector entry. So how this change in the eigenvector entries that is associated with this delta Aij is the change in the matrix element. So if we are removing the A's, delta Ij is -1. If we are adding the A's, delta Ij is 1. So A's removal and A's addition which we are taking. And then we are seeing that this is the formula which we have established, that change in IPR is positive if we have this kind of relation between the pair of the nodes. So there are two pairs of the nodes, R and S is the one pair of the nodes, where we have introduced the link, and P and Q in another pair of the nodes from where we have removed the links. So if eigenvectors increase following this kind of relation, that will give us increase in the IPR value. So if we rewire the nodes in such a manner that we select the nodes P, Q and RS such that this condition holds good, that will lead us increase in IPR. So without doing any numerical or optimization process, just by tracking this thing and rewiring, we can actually increase the IPR, and we have some results. So, but not. X is the eigenvector entry. So Xi is the ith eigenvector entry of PV. So Xi here is the ith eigenvector entry of PV. So, and then T is the evolution time. So time T, so it is related with the lambda max. So lambda is here also in the calculation. So T is with each time you are selecting a pair of the nodes P and Q such that it follows this thing. So P and Q is selected and R and S is connected. So here we are removing and here we are adding. And which pair of the nodes has to be selected? That is based on this expression. So any pair of the nodes, so there may be more than one pair of the nodes actually. So there is no unique solution. So any pair of the nodes which follows this expression, if we rewire, then we get increase in IPR. Okay, so now our this instead of optimization, we can very well perform this thing. So we are rewiring here without doing any optimization, and then we can see IPR is increasing. So this is numerical result, and this is based on analytical calculation. And you can see IPR is going as close to 0.16, and final IPR is also very close to 0.16. But now further iteration, if we keep on doing, then it is decreasing. So this, we don't understand this result, but we are having this increase in IPR. And this result we don't understand because one approximation, which not approximation, we have in the analytical calculation, we have never used that the analytical calculation we are doing for PV. That is generalized. It is for any eigenvector that is true. So there are certain things which we have not taken care because that was difficult. But still we are able to reach to PV as localized or network structure very close to what we achieved from the optimization scheme. So we achieve 60% of the optimal IPR value within 500 iteration, and here you take iteration which is 50,000 iteration, 50 into 10 power 3. So that is the thing, but we don't understand why it is decreasing because maybe we have not incorporated this PV thing and many things. So now this is for multi-layer network. I think how much time I have? So that 15, huh? 5 minutes, okay. So that was actual thing which I presented. Now multi-layer, because whatever I presented, we cannot, suppose a system is given to you, you cannot rewire so much in order to have the desired property. So now only take home thing is that in this multi-layer, if you want to restrict some disease, for instance, so we cannot control the movement of the people so much, or we cannot reroute entire our transport system because my final network was very specific. So we cannot attend that kind of thing. But what we can do, we can create one more layer of awareness. For instance, we can create one Facebook network of the same people, and we can connect that network based on our desired kind of whatever manner we want. We can connect this layer. And then using properties of this layer, we can control the PV localization of entire multiplex system. And this is the thing, and that we have performed actually. We have shown that just by rewiring one layer, not both the layers, we can control the localization properties of the entire multiplex system. And that's why I was saying that now the applications can come to in terms of multi-layer thing, that we are just rewiring one layer and controlling the properties of entire system. So same thing which I have just described, only one layer can be altered or in our control, like you have one accessible layer where we can rewire and one layer remains fixed. Only this layer we are rewiring and the same result, PV thing. Now you can see, if only one layer we are rewiring, still we are getting the same result when we are rewiring both the layers, okay? So we can actually control the YX1, which is the localization properties of entire multiplex network, just by rewiring only one layer, and you can see it is working very well actually. This is for both layer and this is for single layer. This and then you can see that we can achieve localization, we can achieve PV localization as efficiently as rewiring both the things. Okay, and there are certain property which I am ignoring because and single layer, both layer rewiring, and I want to just say this is the importance of optimization, because in the beginning I said there's 3 different components, and here this is importance of optimization and complex network that we know that is the behind success of many natural adaptive process, and the difficulty which lies in the fact that the optimization complexity that increases with the size, and here what we have shown, this is the result which I have not emphasized upon or not clearly explained, but the thing is that rewiring one layer leads to as efficient localization as rewiring both the layers. So it means the optimization complexity that is drastically reduced. So we are only rewiring the small component and achieving something which we can do by rewiring the entire thing. So this 3 layer, 4 layers also we have done, so which is I am finishing, and this is a degeneracy also, which I wanted to emphasize that multi-layer we can get different, we still get degenerate eigenvalues, but we can get rid of also, but I think I should stop the things. This is for various real-world multiplex network, we have done the things, and this is a gist. So we developed a learning framework to explore localization of eigenvectors through an optimization method. And localized networks possess several structural properties, and if we incorporate only one of them, that does not lead to localization. And the most localized network correspond to degenerate eigenvalues, which we are still working on, and we have some more insight into this thing. And localization property is robust against the initial network and is rewiring. And this is for single layer, and this is for multiplex layer. Future direction, like now we have only undirected, unweighted network we have considered, but it would be interesting just to put the weights. Instead of rewiring, we can assign the weights and we can see that whether it can lead to the localization, multi-point localization, for instance. And there are some works where control theory I am skipping, but there are some work which we have done on chimera. Chimera is also, you know, that's very fascinating topic. I saw today very nice poster from Professor Gupte's group on chimeras, and here we are talking about chimera in one layer can be controlled by the tuning the structural properties of another layer. Then explosive synchronization also. So again the same thing, how we can tune property of this layer by changing one accessible layer. So that is the key message. Thank you, and any question?
So in that case, no reflection was there of any interlayer coupling, because you are taking a single monolayer network and simply doing the rewiring job and finding the optimal values. And then when the coupling is absent.
Coupling is interlayer coupling. Yeah. Correct? Huh? Yeah.
Is absent.
Yeah.
These two networks are isolated.
Yes.
And how, without taking in consideration the interlayer coupling, how the other network is being affected by tuning or managing the IPR values of
yeah, I think, yes. So you are right actually. So when we take this layer, we are getting some optimized value. Now we have another layer and we are only rewiring one layer. So this layer actually, that actually applies limitation to how much localization we can achieve. Suppose, yeah, so
yes,
yes, you are right.
You are having 10 number of nodes in this layer, 10 number of nodes this layer. Right? This is having independent eigenvalues, this layer is having independent eigenvalues. So if these two networks are not clubbed together or how they are managed to become a multi-layer network.
No, so if they are not connected, then of course eigenvalues are different. But as soon as they connected, we don't have eigenvalues of this layer or this layer. We have eigenvalues of entire multi-layer system.
I'm talking the same way.
Yes, yes, you are right.
Five nodes on each layer.
Yes, correct, you are right.
10 eigenvalues.
Yeah, 10 eigenvalues. So I am not saying that eigenvalues coming from this layer or this layer. I am saying largest eigenvalue. Largest eigenvalue can come from any of the layer. I am not telling at all that largest eigenvalue is coming.
Largest eigenvalue of this layer, if there is no connection, means there is no relation between these two networks, then how this network is going to affect the other network? Because if there is no connection between these two.
There is connection.
No, if there is no connection, they are not
Then,
affecting.
yes, then how this network can affect this network without any connection?
And there is a connection actually.
There is connection.
There is connection.
Yeah,
Maybe
yeah.
you can show that
Actually, this is
the structure of the network.
Means first network.
Yeah, I think this is the thing. So when you have,
Here.
so now you see there's a connection which is coming with this interlayer link.
That for the network, whole of the network, you are taking this network to
Yeah.
right?
Yeah.
It's okay. And second question is with the rewiring. So can we also, if we take the real essence of the multilayer network, in which there is no restriction that a coupling between the corresponding nodes is there. So is it possible that maybe get better results instead of rewiring one layer, or if we can rewire the interlayer connections also?
Yeah, rewire interlayer connection. Yeah, we have not done, but rewiring interlayer connections. So this I matrix will have different permutations. So we can just renumber these nodes. So one-to-one will have the same result, but there may be possibility you have one-to-many connections that we have not explored. But one-to-one connection, if you connect this with this, you have different this permutation of this unit identity matrix.
Real-time example, because sometimes when congestion occurs in a traffic, like in festivals, all this, then these traffic persons used to divert the traffic. Means dedicated traffic from A to B is there, usual traffic is there, but due to some congestion, they turn.
Yeah, you're right. We have thought once in time, but we didn't actually perform with rewiring because that is just simple permutation, another permutation of the same identity matrix, perhaps.
Maybe this particular question.
Okay.
For discussing later, please allow others to ask some questions. Any other questions? So I have a question that usually happens in an optimization problem of this kind. You get stuck in a local minimum or maximum, whatever is the case. And that you are getting a plateau, maybe just a reflection.
No. So that's what I said, that we use actually simulated annealing kind of thing. So in the beginning, we accept wrong connections as well. And then slowly we cool down the temperature. So that all happens in the beginning. That's so in the beginning. Yeah. So that we have taken care of. Actually, it doesn't stuck into local minima also so easily. That was also we discussed once one point that why it doesn't. This is a very easy optimization. Like it doesn't stuck actually into local minima so easily.
I see.
So I think it is. I don't know. Maybe some more.
Any other questions?